Hello everybody, good to see you. Welcome to Ask Math Anything. And I see that there are already over 100 people here today, so it must be a good day. If you're new here, welcome. What we're going to do is we're going to talk about all kinds of random questions that the audience asks, and we will try to make the difficulty level kind of understandable to people who are studying algebra or geometry. Now, those of you who have been here before know that I say that every time. And somehow, I do a terrible job of choosing questions that are actually understandable to people who are doing algebra or geometry. And I'm going to try to do a better job today. So let's see. I see that some people have said a comment about how the sound seems low. Is that true? We'll see. So I'll try to speak up a little bit, and if that doesn't work, we'll mess around with the settings. But I don't exactly know how YouTube's thing is working these days. Sometimes YouTube makes some adjustments to somehow make things louder or softer. And I do see that people were asking about, what happened yesterday. That means we've got some regular watchers. Well, welcome back. So, what should we talk about today? Let's see. So I'm looking at these things because now I need to be more careful. Last time I had some crazy questions and they were too hard. I see that somebody named Rated R has asked me to square an enormous number. I'm looking at your number and I don't see anything particularly nice about it. So I'll say, I'm not really sure I can square that one nicely. But let's do something else instead. Since you want me to square a number, does anyone know what happens if you decided for fun to square this number? Does this look like fun? Do you think anyone wants to do this problem? Oh, this is going to be terrible. I'll have to multiply two 9-digit numbers. Who in the world would want to multiply two 9-digit numbers together? Oh, it seems like some people do. Well, who has an idea? Is there a nice way to do it? Oh my goodness, Rithik already has an answer. Tian Michael has an answer also. It's because this is not bad at all. You see, let's not do 9 digits. Suppose we were really lazy. And suppose what we wanted to do instead was the 4-digit version. Hey, let's get some more space. Suppose I wanted to do the 4-digit version. Do you know what happens when you try to square the 4-digit version? You run out of space, but I'll try to do my best. That's 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. And when you add, oh my goodness, 1 2 3 4 3 2 1. So what do you think happens if you square that one? Well, I see that a lot of people have already written the answer. There are 9 ones, if I counted right. So it's just 1 2 3 4 5 6 7 8 9 8 7 6 5 4 3 2 1. So you wanted me to square a big number. I want to square that one instead. And let me give another tip. So some of you in the United States play in a math competition called Math Counts. The way Math Counts works is that you do a bunch of problems, and then at some point there's a round where some of the top 10 students go in front of on a stage or something for everyone to watch, and they get really nervous because hundreds of people are watching them try to do math problems as fast as they can. And now here's a tip. If you ever saw this problem in that countdown round in Math Counts, do not attempt to say the answer as 12 quintillion 345 quadrillion 678 trillion 987 billion 654 million 320. Darn it! I shouldn't have started on quintillion. Do you see? You see why that's bad? The reason it's bad is because if you start saying it from there, then it's like, oh no, I got the answer wrong because I just started saying it and it was the wrong illion. It should have been quadrillion. Yes, so don't do this. If you ever get this kind of a problem, the correct way to answer the problem, if you have to hit the buzzer and answer it, is to say 1 2 3 4 5 6 7 8 9 8 7 6 5 4 3 2 1. So that's a very important tip. If you're ever doing this contest in the United States, never make the mistake of saying 12,000. Oh, darn it, I meant 12,000,002. Right? And any of you who like to play in the spelling bee know that I think it's the same principle. Somehow once you start saying something, you have to stick with it. Actually, I guess if you play chess, it's the same thing, right? Like if If you move a piece, you can't usually take it back. Is that right? I don't really play chess. But okay, more questions. What else can we do? Leo Z asked, why is 0 so famous? 0 is famous because it's really useful. Actually, if you're thinking about what you want to do with numbers, the moment you decide that you don't want to write numbers like this, what's that? Does anyone know what that is? People are talking about chess, touch move, right? Same principle. But what's that? What's XM? Anyone know what is XM? XM is the wonderful way that Romans decided to write numerals. It's not 90. It's 990. Wait, actually, is that right? Now I'm a little confused. I have a feeling that you're not actually allowed to do this. My guess is that you're not allowed to do this. My guess is that if we had a proper Roman here, anyone Roman? If anyone's Roman, please speak up and tell me how to write this. But I have a feeling that it's actually supposed to be written CMXC. I think that's actually what you're supposed to write. Yeah, people are saying you're not allowed to do that. Yep, CMXC, that's correct. Clearly, we got some Romans here. Somebody asked, why are you not allowed to do it? Because I believe that the Roman numerals were such that you can only use like the smaller before the larger when it's like just smaller. You see what I mean? Like the X is 10 and the C is 100. So you can put the X next to the C. And then the C is 100 and M is 1,000. So you can put the C next to the M. But you're not allowed to put the X next to the M because the X is like a 10 and the M is like 1,000. So for whatever reason, they decided that, you shouldn't do that and you have to do this instead. But you see, if you think about it, how would you write a number? This is a completely reasonable way to write numbers. It's just like somehow you put this. This is basically like glorified, what are they called? Tally marks. That's basically what the Romans did, The Romans were just like, here's 1, here's 2, here's 3, 4. Too hard to write those 4 things. But, roughly speaking, that'll be 4, and then somehow, if we had 5, you would sort of do this kind of tallying. But maybe the Romans thought this tallying is too complicated. So instead of this thing, they just wrote 5. That's like this, right? This is the same. And then the 4, they were too lazy to write 4 lines. So they just went this. And you know why Romans might have been lazy? The reason why Romans might have been lazy is because, does anyone know like where you saw these numbers? Actually, this is worth knowing. Does anyone know like what you do? Where do you typically like write these numbers? Anyone know? Music theory, Super Bowl. No. I meant like Romans. What did Romans do with these numbers? Like Romans actually wrote their numbers somewhere. They banged them onto buildings. Like they carved numbers into buildings. What I'm trying to say is, if somebody told you to go and bang some stuff into buildings, would you rather bang this thing into a building or the V? It's obvious you'd rather bang the V. It takes you a lot of work to bang the number into a building, right? It's into stone. So like it's a huge deal. The fact that you can save so much banging, this is just so much better, right? So this is actually, I'm actually being semi-serious here. If you look at the way the Roman numerals and the Roman letters are, Roman numerals and Roman letters are made of a lot of very straight things, sort of. Actually, I just made that up. That's not really true. There's like a C. But anyway, they're kind of generally like more straight-ish. If anyone looks at the script, if anyone looks at the writing style of, say, Arabs, the Arabic language, if you not Arabs, if you look at the Arabic writing language, the Arabic writing language is like this. Do you know what I mean? Has anyone seen the Arabic, like anything written in Arabic? There's like lots of like curves, right? And that's because they didn't have to bang everything into stone. Actually, they did a lot of writing. They did writing, like I think on paper or other things. It's like if you're writing, it's okay to have these curves. But if you're banging into stone, you don't really like curves. Curves are not much fun. So anyway, people are asking what's the big deal about 0? The big deal about 0 is that if you've got this going on, yeah, I guess you could write numbers this way, but it's really inefficient. We talked about in another live stream before how you would ever try to do like a calculation, like adding numbers or multiplying numbers or long division, for goodness sakes. Then you need to use place value, and that's where 0 is really useful, because for place value, I want to say the number 1001 I need to say, 1001. I have to put something in there. I can't just go like, that's 1001. Don't you agree? Looks like 1001. Doesn't look like 11, does it? So there's got to be something in there. But how do you know whether it's 101, 1001, or 10,001? That's why you have zeros. Zeros were invented for place value, as well as meaning like you have nothing. Both of them are useful. All right. People here apparently have figured out a way to write Arabic. I myself have a lot of trouble reading Arabic. I actually can't read Arabic. It's too difficult in the sense that I never quite learned how to piece things together. All right, I see that some people are counting in Roman numerals. Let's do some more problems. Yeah, K-Chu says, can't you use some kind of overline, underline on Roman numerals to make them represent 1,000 times what they usually do? Yes, you can. But at the same time, it's not fun to do like long division with Roman numerals. I mean, I would challenge anyone who wants to go and play with Roman numerals. It's like, it is no fun to do this. Who wants to divide that? Does anyone know what this is? Does this look like fun? Oof. Oof is correct. Although there is an answer. Do you know what the answer is? What do you mean 77? No, it's not 77. It's LXXVII, everybody. That's the answer. So as you can see, Romans were probably not very good at long division. This is just terrible. Right? I think I got that right. This is 1001 divided by 13 is 77, because 1001 happens to be 7 times 11 times 13. But you could imagine if somebody gave you your math homework and said, please do a whole lot of things that look like this. No, thank you. All right, let's see. What other questions are here? Tempai D says the big deal about 0 is that the Romans didn't have it. Satya Memi asked, anyone know what a 360-sided shape is called? That's interesting. What's a 360-sided shape called? I have no idea. I mean, dodecagon is 12-sided shape. But I don't know what is the prefix for 360. So I'm not sure I would be able to answer that question, other than 360 gon. Yes, I think that's actually what I would say. 360 gon. Sounds good. I like how Anna House says, almost a circle shape. I think that's also pretty accurate. Oh, interesting. So Ayush DM said, squaring all these ones where I have up to 9 digits is a great trick. But what if I had 11 ones? Oh no. 1, 1, 1, 1. I should be counting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I have 11 ones. Oh no. Why did you choose 11? It looks like I just wrote more ones. Looks like I'm doing tallying. Maybe I went back to Roman times. What's this? Well, obviously, it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? Well, almost. It's almost that. You see, that is the answer. The answer is 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to do like some colors just so you can tell things apart. 9, 10, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What did I do? I squished some numbers on top of each other. Do you know why? It's because of the same reason that I was able to say 1, 2, 3, 4, 5, 6, 7, 8, 9 before. Remember, if I'm actually squaring this, I'm going to write down this like 1 through 11, and then I'll shift it, and 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 I'll just keep adding in those columns. So there will be some columns where I'll be adding more than 10 things together. But that's exactly what this means. You see, at some point I had the 11. I think the 11 is here. It's like the 1, 1. That's the 11. But remember, when you actually add in a huge stack, you carry. So I wrote the numbers on top of each other because what I'm going to do next is I'm going to merge together the numbers that got written on top of each other. So that's equal to 1, 2, 3, 4, 5, 6, 7. Oh, this is tricky. I would want to write 8, and then that 9 and the 1 smushed on top of each other make a 10. Okay. But then the 1 and the 0 squished on top of each other make a 1. The 1 and the 1 squished on top of each other makes a 2. And then it's a 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. Did people follow what I just did? What I just did is I said it's sort of like I just stacked these things together and I added them, but I need to carry, and I have to carry over to this part. So now I also had another carry happen. There's a 8 with a 1 smushed on it. That's okay. We'll join them. 1, 2, 3, 4, 5, 6, 7. That's a 9 now. 1 plus 8 is 9. Okay. And then 0, 1, 2, 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I think that's the answer. It's not actually that bad. So in fact, when you're doing any of these things where you're squaring like a whole lot of ones put together, all you have to do is just like stack them and add, and occasionally do some mushing around to carry in the middle. Okay, next question. Okay, here's a question that is full of lots of different facts. And so we're going to write this down and see what we can do. Good gracious. How old is your son? Asked a man to his neighbor. So the question was, how old is your son? And then here's the answer that came from the neighbor. Okay, the neighbor says, my son is 5 times as old as my daughter. So son is 5 times as old as daughter. Okay, that's one fact. Looks like daughter is flying up to the right. Let's do this. Son is 5 times as old as the daughter. Okay. Wife is 5 times as old as my son. Okay. And we also know that I am twice as old as my wife. What I'm writing in green, green is what the person is saying as the answer, okay? Green is what the person is saying as the answer. And my grandmother, who is celebrating her 81st birthday, is 81, and is as old as all of us put together. Okay. Does this work? Let's find out. So this is the question. How hard is this question? Probably set up equations. Yeah, let's see what happens, okay? So first of all, let's double check. Is this a trick question? How many people are here? Well, there is a son, there is a daughter, there is a wife, there is an I, and there is a grandmother. Okay, by the way, here, I'm going to tell you, I don't want to set up equations. I'm lazy. What I'm going to say is I'll first see that everything here is about multiplying. If everything here is about multiplying, let me just make up some fake ages right away. If the son is 5 times as old as the daughter, let's just pretend that the son is 5. So 5 is the son. And let's say the daughter is 1. And now wife is 5 times as old as son, so that's 25. I am twice as old as wife is 50. Wait, that wasn't I, that was wife. Oh, it works. because that's 75 plus 6. It's actually 81. So you're all done. That's the entire thing. Okay, let me tell you why I did it this way. I actually didn't know that this would work. What you actually want to do is you should just go and do all of this part first, get something, and if you found out that your answer added up to 27, you know what you would do? If the whole sum is supposed to be 81 and it added up to 27, what should you do? Skylar, this is not guess and check. I actually don't want to use guess and check. What I'm doing is I'm observing that in this problem, everything is about multiplying. If everything is that something is a multiple of something else, something's a multiple of something else, something's a multiple of something else, then if I just anyhow choose some numbers that work for all of the top part, then all I need to do is to make grandma work, is I need to see what I multiply by. And everyone here has answered. If I had done all this and I said, hey, look at that, it adds up to 27. How annoying. It was supposed to add up to 81. Then I would just triple everything. And when you triple everything, then you'd get the sum to be 81. And also all of these would still have the right ratios that they did before. So this is actually not about guess and check. This is about observing. It's all about ratios. So you can just anyhow put some numbers down. Okay. Let's see. What other questions do I have? Oh, this is interesting. Immortal Banana. How are you choosing these names? You know I am recommending bananas all the time. Is that related? Anyway, so you said, if my eye sees things at 30 frames per second, why is my 40 frames per second video game laggy? Oh, this is a good question. This is a good question. So what does it mean to be 40 frames per second? If your eye is seeing things at 30 frames per second, like why would it seem laggy at all? Well, it has to do with, if you're able to see at 30 frames per second, it would look a little odd to you if you saw 2 frames and the frames weren't really going at the right speed. How do I explain this? That's actually a really good question, because I have a problem right now where one of my monitors in this office has a frame rate mismatch, and that frame rate mismatch can make this make sense for you. So here's the deal. So suppose what's actually going on is that your eye is able to tell what's going on at about 30 frames per second. Now you're saying that your computer is able to show your video game at 40 frames per second. What 40 frames per second means is that maybe in your video game, what happens in a video game? I don't know. That's a screen, okay? And inside your video game, maybe what's going on is that there's some clock moving around. I'm just pretending that. Okay, so I got a clock. So there's this clock going on in your video game. And so this thing happens. And then it's 40 frames per second, right? So 1/40th of a second later, you get a nice picture over here. 1/40th of a second later, you get a nice picture like this. Oh, wait. Actually, clocks don't go that way, do they? Clocks go the other way. That's why it's called clockwise. All right. So you can tell I do too much math. Unfortunately, in math, we usually make our angles go, the other way. But that's right. I did say it was a clock. Okay, so if it's a clock, clocks are supposed to go clockwise, okay? So here we go. This is a clock, a legit clock now, okay? So that's one frame, this is the next frame. I see people are appreciating my art. But anyway, we'll make do with this. So this is one frame, this is the next frame. And the next frame that happens in your wonderful video game, apparently this video game, all it shows is a clock. I'm not sure how this is fun. I mean, some people used to say that if they're bored, all they do is stare at the clock. But, this is just happening. The clock is going along. It's just coming along here. And then the next frame is like this. So, it's just kind of going along. Now, if what happened is that you actually had your eyes kind of blinking and only looking at 40 times a second, if you're blinking and looking at 40 times a second, then what would happen is that you would see this. 1/40th of a second later, you'd see this. 1/40th of a second later, you'd see this. 1/40th of a second later, you'd see this. Okay? Yes, people do think that my video game is kind of boring. It's just a clock. But now, if what happens is that your brain is not noticing 40 times a second, but only noticing 30 times a second, you're not going to see every one of these. Do you know what I mean? You're not going to really register all of these. That's actually not how vision works. I shouldn't say that your eye is just like snapshotting, but I'm just giving some example of how if you're playing this epic video game of watching a clock move around the correct way, hey, okay, maybe at least I should have made the clock go backwards, so then that would be epic. But anyway, if you're looking at this particular video game, if you're not registering every single picture, you know what happens if there are 40 pictures and you only see 30 of them? If there are 40 pictures and you only see 30 of them, you might first see this one, then you might see this one, then you might skip over that one, and then you might see this one. What I'm saying is that it would look a little jerky. It'd be like, hey, clock, what happened to you? You went from here to here and like that? Do you know what I mean? It's like here, here. How did you jump? Well, the way you jumped is because somehow it's uneven. Sometimes you're actually seeing the next frame, and sometimes what you notice is like the next frame, and then somehow it's like it's all jerky. This is actually why people say that if you want something really smooth, do you know how many frames per second you actually should aim for? Do people know? This is first of all why people care about 60 frames per second. 60 frames per second, now it's sort of like, all right, there are just so many of these frames that you actually see this one, and then then you skip at least one, then you skip at least one. And somehow it looks like I've made a best-selling game here. We should clearly put this game on the App Store. Everyone can stare at the clock, right? But what I mean is if you're at 60 frames per second, it's a little bit more resistant to this, because at least it has, you're not going to be so bad where sometimes you have barely any motion, and then you have, when I say barely any motion, it's like 1 frame's worth of change and then 2 frames worth of change. See, that's when things look jerky. It looks jerky when the clock, our wonderful clock here, it moved 1 bit and then suddenly it moved double, right? It's like, how can it be that from 1 frame to the next, there's like a difference of a factor of 2? But if you're at 60 frames per second, you're not going to get a change of a factor of 2. Do people get this? It's like if it's 60 frames per second, you either go 2 frames or you go 3 frames. And so the ratio is what matters. Then basically the biggest ratio you get of the mistake of the clock moving is like 2:3, which is like 2/3, as opposed to 1:2. Did that sort of make sense? That's actually why it gets better once you get to 90 frames per second. If you're at 90 frames per second, then like somehow from one to the next, you're going to go either 3 frames or 4 frames, right? Something like that. I actually say that because people think that the eye actually sees a little bit slower than 30 frames per second. That's why the movies are shot at 24 frames per second. So somehow, if it's like 90 frames per second and your eye is able to see around 24 frames per second, then somehow these gaps are either 3 frames or 4 frames. Now the ratio is even better. So exactly, P14, Y, R0, and 3. Higher FPS is better because the ratio between how much went in a successive frame to what you noticed is closer to 1, right? It's like somehow instead of something where it could have been 1 frame difference or 2 frames difference, which is huge difference. Like the clock could go from here to here versus here to here, right? But if you have more frames per second, then it could be that, at 90 frames per second, we're talking about 3 frames for 1 jump versus 4 frames for 1 jump. And 4 divided by 3 is closer to 1. And if you can go even faster, 120 frames per second, that's pretty good. 120 frames per second, suddenly you're talking about 4 or 5. And that's why this works. Right. So that's the main thing about these frames per second. And what happens if you go at -1 frames per second? I think that's called going backwards in time very slowly. You want negative frames per second because then that would be the epic game, right? If you go negative frames per second, then my clock will move like math, and it will actually go the right way, which is like that way, going around the circle. All right, so I hope that made some sense to you. That's how frames per second works, and that's why actually when you're making like a web app, what you really want is you want to target 60 frames per second, because that's the one that feels the most smooth to the average person. Okay, more questions. Oh, Brian Lee asked, what frames per second is our life going at? That's a good question. This is an area called quantum mechanics. I myself don't know enough about this. I vaguely seem to remember at some point somebody might have said time is even quantized. I'm not sure. If time is quantized, then there is a certain notion of frames per second. But oh wow, no name, you're pretty good. You said seconds aren't certain. That's also true. Because like if I have different people observing at different times, time moves at different speeds when you're moving really fast versus somebody watching you. So I think I'll say some people believe that I think not some people believe. I think that the theory is that it is quantized, time is quantized, but the number of frames per second is so ludicrously large that you don't notice it. You don't notice it. But I believe it's actually not infinity. I'm actually not an expert on this, but I believe it's not infinity. Carbon News asked, what FPS is this video? Well, here's what we're doing. There's a camera there. The camera is set at 29.97 frames per second. This is exactly what we're sending to YouTube. Don't you think it's a great idea that we send things at 29.97 frames per second? Hopefully some of you are wondering, why in the world did you choose 29.97? What should I have chosen? Why not 30? Yes, Vera, you're right. Why not 30? Actually, does anyone know? Does anyone here know why 29.97 is used? There's actually a story here. There's a reason why 29.97 is used. It's because this was used, why not 60? So first of all, the more frames per second that you do, the more data that's going out. So for example, from that camera right now, the data that's going out of that camera into the computer to stream outside is transporting at, well, I can tell you how much data I fill up. We record 250 gigabytes per hour. So that's actually how much data rate is coming out of the camera. So the camera is making 250 gigabytes per hour, and that's at this 29.97 FPS. Yes, indeed. Like with all of these live streams, we have these huge hard drives in this studio that are just filling up with the live streams, because every single live stream I do fills like 1/4 of a terabyte. So you can do the math, and you can find out that pretty soon you fill up like 16 terabytes. But in any case, if we wanted to send it at 60 frames per second, every frame is like it's like a picture. So I would be using 500 gigabytes an hour if we were doing 60 frames per second. Oh, that's why you delete the videos. Well, actually, we don't quite delete the videos. We are saving all the videos here in this office so that at some point in the future, we might go and make some kind of a show out of this. We'll see. If we ever make a show out of this, I think all of you who are on the chat will be famous, because everyone will be like, hey, who's this temp ID person? I wish I could meet temp ID, or something like that. Okay, but now, why is it 29.97? There's a reason here. It's because a long time ago, people used 30. They used 30. So now, how did it become 29.97? Now, Wikipedia is a better source than me on giving you this story, but at some point I went to look at this, and if I remember correctly, the reason is because 30 FPS is how you'd send just the video. But at some point, people decided that they wanted to not have silent films anymore. It's not that it takes less data, it's because they used film. Film, like film. Film is this thing. It looks like this, and it has like all of these things on it. It looks sort of like a ladder. Film. That was film. And somehow, well, I guess this was not related to film. This is about transmitting it over the TV. Old school. I love how you guys call it old school. But anyway, so there used to be this thing in the world called film, all right? And this thing called film, human eyes became worse. People are very funny here. But somehow, the way it works is you were sending at 30 frames per second. You were sending just the picture. But at some point, people wanted to also have sound. So if you wanted to also have sound, you would have to have some way of, I guess, being able to pack enough information in. So my understanding is that this 29.97, it's actually because it was something sending at 30 frames per second. 30 frames were still going every second, but basically like 1 out of every 10,001 contains sound information. That's what I seem to remember. I might be wrong. But basically what was going on, I think, is that things were actually being sent at 30 frames per second, but 1 out of 10,001 of the frames contained something else. I think it was audio, but I'll just write something else. It's because you might need to have some sound or something like that. And now why is this 1 over 10,001 relevant? It's because then if every second, 30 frames go by, then, but this fraction of it is something else, then actually the real frames per second is going to be, oh, maybe it was 10,000. That's a good question. Is it out of 10,000? I vaguely remember it was out of 10,001, but I may have forgotten this already. It might have been like 10,000 frames followed by one sound thing. I may be wrong. Or maybe it's 1,001. It's looking more like 1,001 to me than 10,001. We're going to find out soon. Here's how we're going to find out. Wait, yeah or no? Let's see. I think it's 1,001. We'll find out soon. The way that you find out is we'll just do a calculation. What is 30 times the stuff that doesn't contain something else? Does anyone know what this is? This one requires some kind of a calculator. 30 times 1,000 divided by 1,001. And you're right, maybe it's 1,000 instead. Is that right? Yeah, I don't quite remember. So now I'm thinking about this. Is that the way it works? I don't exactly remember anymore. But if you do 30,000 divided by 1,001, oh yeah, so I do remember. Okay, so the thing that I'm remembering is I remember that this is actually a fraction. 30,000 over 1,001. Okay. Oh, and that's exactly what this is. This is 30,000 over 1,001. So I do believe this actually works out. If people actually calculate this temp ID, you're saying it's 29.97. So that's exactly what this is. And I do remember from video editing, when I do some video editing occasionally, I see that it looks like something like this. So for whatever reason, this is like an artifact of how it is in this world. And if you're asking who invented this stuff and why did anyone ever bother, it's because when you have this world and a standard becomes used, meaning a lot of companies or broadcasters start using something, it's very hard to change the standard. And then things just get locked in there. So for whatever reason, professional grade cameras usually shoot at 29.97 FPS. Oh, it's 1,000, is that right? So you're saying, is it 1,000, not 1,001? So you may be right. If this is 1,000, then the FPS would end up being like 30 times 999. Philip, you may be right. I'm going to say I'm not entirely sure about this. You guys can check the internet on that. But the basic idea is one of about 1,000 frames are going to have something else. Although there's a bit of me that seems to remember it was actually divided by 1,001. But we can worry about that differently. That doesn't happen to be mathematics. That's just like random stuff. Okay. Amy Lee has asked, how did you get the idea to start this live stream? It was really just because I heard at some point in the middle of March that people had to go home and not go to school. And so I thought if people are not going to go to school, maybe I'll provide some kind of a fun math stream if anyone wanted to see this. Of course, you could also see your teacher teach math, which is also good. But I felt since people were at home, I may as well throw this out here. Because of coronavirus. Exactly, Vera, exactly. It was because of COVID-19. I decided to just go and put this thing out there. And then once we started doing it, we just kept doing it because we saw people coming to the live stream. We still have some people coming to the live stream. Okay, more questions. Vera Wang, I'm about 79.92% sure that Professor Loh won't notice this. Yes, but the moderators did, and then I noticed it. Oh, Tong Tong Chen says, today is my birthday and I have a problem about it. Happy birthday. If there are 200 people watching this live stream, what is the chance that at least 2 of them have the same birthday? So you're saying there are 200 people watching this live stream. What's the chance that at least 2 of them have the same birthday? This is huge. This is huge. This thing would be the chance that they don't have the same birthday. We already did this kind of calculation before. The chance that there's no 2 that have the same birthday at like 24 or 25 people is already like a half. And so if I have 200 people here, the chance that there's no common birthday, I would guess that it's like less than 1%. Now, if I wanted to know for sure, what's the best way to do this? I'm thinking to myself, what's the best way to do this? It's not very easy to do this calculation, unfortunately. I mean, if I wanted to do this calculation, what we'd have to say is, what's the probability? Let's assume, well, you know what? We've got so many people here. There might even be somebody who was born on February 29th. For privacy purposes, you do not need to say your birthday in the chat, okay? So don't feel any obligation whatsoever to say your birthday in the chat. But, you know, I was going to say there is actually some chance that we have a February 29th birthday in this chat. But for this problem, let's go and assume that doesn't happen, okay? So what I could say is assume that there's no leap year problem. So then the probability that all the birthdays are different, because that's what I would like to say is a very small number. Well, that is, there's the first person. The first person, you don't care. Whatever birthday is fine. The second person would be, oh my gosh, P14, 3YR0N3. Don't tell anyone your birthday. You need to protect your privacy. Don't go telling everyone your actual birthday. Now everyone knows you were born on February 30th. Okay, let's keep going. So 364 over 365. And we keep going. And yeah, that is a lesson. Never go and talk about your real birthday on the internet, especially not on some random person's chat, okay? But let's keep going. So yeah, okay. People all caught on pretty quickly. February 30th does not exist. Hopefully someone here can go talk about their birthday, which happens to be on like, you know, on, what is it, April 31st. April 31st is a pretty good day too. Anyway, we keep going. So there are 200 of these, right? So 200 of these. And it's over 365. Oh, what's the numerator? Whenever I do this thing, I always am afraid of being off by 1. And here's how I look at the pattern. The first one is 365 minus 0. The second one is 365 minus 1. And that's the second one is 365 minus 1. So this 200th one is 365 minus 199. Or it's 365 minus 200 and then add 1. That's easier, 166. Okay, who wants to multiply this? Not me. What's the best way to do this? Okay, I'm going to do something weird. So, I mean, I know that you guys have calculators, you guys have computers. I don't. I mean, I want to see if I can do this with just a calculator. And I don't know. Should I do that? I did promise I was going to do something easier today, not something hard. So I can tell you what I would actually do, which now is not really doing it easier, but it is maybe doing it a bit harder. This is actually equal to 365 times 364 times all the way to 166 divided by 365 to the power 200. Now, what I want to do is I want to say, if you had a computer, yes, you could do it, but there's a way to approximate it without a computer, which is actually pretty sophisticated, but I'll just give you a little idea of, like, I'll give you a taste of what's involved here, okay? The top, who likes to multiply all those numbers? Not me, but there's a trick you can use. The trick is to say, you know, if I actually wanted to multiply 365, well, let's flip it around, okay? If I wanted to multiply 166 times 167 times up until 365, the answer happens to be e to the power log of 166 times 167 times 365. Ooh, okay, something happened. So e appeared. What is this e? So e is this like this weird number, okay? E is this weird number, 2.718281828459045 and something else. That doesn't look like a 4. Some weird number. Now, why would I do this? Yeah, isn't this harder? This looks like I did something stupid. Why in the world would you use e? And then now you got this crazy ln. What does ln mean? Ln of a number just means, hey, e to the what is that number? So what I just wrote down here is actually just like a fact. I mean, there's nothing special here. It's just like blah, blah, blah equals e to the log of blah, blah, blah. Well, of course, that's the definition of the log. Well, there's something nice about the log. The log is something where if I want to know like what power do I raise something to, well, if I multiply things together and then take the log, is the same as the sum of the logs. Okay, so what's going on is that the next thing that's going to happen is this is equal to e to the power log of 166 plus all the way to log of 365. So this thing here, what I've just done is I have just used the fact that if I want to know, like, what power of e is 166? I don't know. What power of e is 167? I don't know either. But if I want to know what power of e is 166 times 167, it'll be the sum of those two powers. Okay, we actually talked about this a little bit earlier in this live stream, like, way, way, way back, like maybe like 2 months ago, about logs. Now, why is this useful? The reason this is useful is you can actually approximate that. So it turns out that if you want to add up all of these logs together, there is actually a way to know approximately what is the sum of a bunch of logs. So now what I'm curious about is, what is log of how much? 166 plus log of 167 plus up until, whoops, actually wait a second, I wrote the parentheses the other way before. So log of 166 plus log of 167 plus log of 365. Gee, it would be really nice if I could figure out what that is. You have no idea what you're seeing. Okay, so what you're seeing is that somehow I want to know what power of e is this, what power of e is that, what power of e is that. Okay? And since we've now gone over the heads of some people, I'll do this really fast. So if I want to know what this is, see, here's what you do. You just draw a little graph. You draw a little graph. Here's the graph. Whoop, whoop. You know what log looks like? Log looks like this. Whee. This is log. Okay? And what I want to do, that's log x. What I want to do is I kind of want to know a bunch of areas. See this thing? This is at 166, and the height of it is at the log of 166. And then I'll do another one. Here's another one. And that one happens to be at a height of 167. Now I'll draw all of these rectangles. What am I doing? Yeah, yes. So Tony Lu sees where this is going. So what we're doing is we're doing some crazy integrals with a bunch of people who are watching from middle school. But that's okay. I'm trying to show you how this is useful. It's like if I wanted to go and add all of these together, I want to know the area. If I want to add up all of this together, this is the total area of this part I've just drawn. So that is equal to the area under ln x from 166 to 366, approximately. And this thing happens to be solvable with calculus. You may have seen like weird symbols like this before. Integral 166 to 366 of ln x dx. I know that this is way beyond what you normally do with like algebra or geometry, but I'm just trying to show you like this is why someone might care about logs, and we'll actually get an answer out of here. Okay, so then when you get this, what is this integral of this? This is like x ln x. Oh, I already forgot. Is it minus or plus? I think it's minus. We'll find out soon. Anyway, x ln x plus x is x times 1. Yeah, I think this is right. Okay, and then you evaluate this thing from 166 to 366, and I'll tell you an answer now. The answer happens to be 366 ln 366 minus 366, and then minus, actually let's do it this way, minus 166 ln 166, and then the other part becomes minus 200. Okay, now what in the world is going on? We got the answer now. So what do I mean we got the answer? The answer was e raised to that power. That's all I care about. E raised to that power, and then we're going to have to divide by 365 to the 200. Okay? So I have an estimate. The question that you asked is about e raised to the power 366 ln 366 minus 166 ln 166 minus 200 all over 365 to the power 200. Does anyone know what this is? Right. So this is actually what I estimate the answer to be. Oh, yeah. You know what? With this e's, I actually have something else I can do. The e raised to the thing, let's simplify it. This is equal to 366 to the 366 divided by 166 to the 166 times 365 to the power 200 times e to the power 200. So that is my answer. This is actually my answer. If anyone is able to do something with a calculator, you'd get something, and it would actually probably be pretty close. Now, what in the world happened here? I actually used this screen just to show you that weird stuff can happen that is actually really, really useful. Seems interesting. How interesting? Now let's talk about why and like how one would think of this. Okay? What's actually going on here is that we had to do something awful. We had to go and figure out what is this big product. Who in the world wants to multiply all this stuff together? Nobody. But it turns out that if you switch it into logs, it turns into addition. Because log is just asking, like, you know, what power do I need to take to make this number? And so just as an example, since we had some logs just appear, if I use log, log base 10, of something like 1,000, that's equal to 3. That's like 10 to the power 3 is 1,000. That's what log means. And by the way, log of 1,000 is the same as log of 100 plus log of 10. That's equal to 2 plus 1. And that's also 3. But the reason this makes sense is because what's actually going on is the log is just saying 10 to the power what? Oh, by the way, I'm now talking about something that should be understandable to everyone. So we're pulling down from this like crazy calculus thing we just did, and we're coming back down to something that's like, you know, I basically wanted to show you we can go pow and get an answer. And then now let's pull it back down, right? We went all the way and got an answer, and it's like, wait, how did we get there? And now let's go and see these steps that get there. The first idea was that the log is just something which says 10 to the power what is that number? That's the log log. The ln log uses a number called e. But the log log, if you look at that, 10 to the power what is 1,000, of course then it makes sense that 10 to the power what is 100, 10 to the power what is 10, if you add those two powers together, it's like 2 plus 1 makes 3. So this is actually one of these log rules. Log of something plus log of something else is the log of their product. Okay? And that's what we used here. And now we just found out we have to figure out what in the world is the sum of logs. And the nice thing about the sum of the logs is if I now draw a picture, and I just draw this picture with this ln, then I just draw a bunch of little rectangles. The width of every rectangle is 1. That was 166. This is at 167. That's the x-coordinate. The next one, the next x-coordinate is at 168. Okay? If I draw all of these little pictures where I have these little tiny rectangles and the width of the base is 1 and the height is, it just goes up to the log function, then the height is like log of whatever I stuck in. So since this was 166 here, if I go up and I touch the log function, the height is log of 166. Now once I have this, the sum of the logs is just the sum of the areas of 200 rectangles. And now the useful thing about the 200 rectangles, you're asking, is this a theorem? Please tell, I'll check it out. So I don't know if that was a question for me, but I'll tell you the theorem that I'm using is basically that if you, the name of this theorem, okay, if you want to know what to search for, what we actually just did here, this thing here is something that is called a Riemann sum. That's actually what we just did. This is a Riemann sum. A Riemann sum is what happens when you go and say, I've got all these little rectangles I'm adding together. I wish I knew their area. But the way you get their area is you'd approximate it by something called, hey, this log thing, let's just find the area under the log thing. It is an approximation. We waste some of this little bits of area because it's not actually like flat on top, right? The log thing just keeps curving. And I'm saying that I really care about the sum of these strips. And instead of getting the sum of the strips, that's too hard, we'll actually find the area under the whole smooth function. Now you might say, hey, that looks like it's harder. Now you got to find a curvy area. But it turns out that the ln function is one which actually has a way to undo and get the area. This squiggly, all this squiggly means, maybe you can even imagine what this squiggly means. The dx is just some notation. Don't worry about the dx. Ultimately, there's just a squiggly, and there's an ln x. The squiggly is called a squiggly because it looks like an S. It looks like an S for sum. You basically want to sum up the area under here. So if you ever see a squiggly thing, right? And actually everything I'm talking about right now is not something that's using advanced math yet. There will be one point that it gets really advanced later. But like this thing of the squiggly, if you ever see a squiggly like this, the 166 means starting here, starting at 166. The 366 means ending here, okay? So what's actually going on is it just wants to know, the squiggly means from the starting until the ending, what's the area under the curve? That's actually all this means. So now what we have to do is we just have to know, how do you figure this out? And one of the breakthroughs in calculus was that you actually can take this squiggly thing and turn it into that. And that only works because you happen to have the ln instead of the log. This is now too hard. Like this particular piece, how did you know it was this? That's too hard. But you know, this thing, once you've got it, you can calculate an answer, and then you'll be done. Okay, right. So I hope we didn't scare too many people away. Some people got a little confused, but I think what I wanted to put here is that if I was multiplying lots of things together is sort of like adding lots of things together if I take the log first. That's like the main idea. Okay? So if you take the log first, then you add everything together. I see that somebody said, let's make this math live stream simple, and then I went into an integral. Oops. Okay. So, but there's a reason I wanted to do this. I only wanted to do this at the end because I wanted to show you how, you know, whatever you're doing with math could actually go somewhere that can even answer one of these questions. You know, like you asked me a question, and if what we tried to do is if we said the only way to do this is to go and type all those things in on a computer, that's like really hard, right? But instead, it turns out that there's a very powerful tool that if I wanted to do a lot of multiplications like this, then you could actually do it with an addition instead. And that's what this is. So this is what hopefully you will learn at some point. You will learn it. You will learn it sometime. Okay, I see people want easier math. You got it. You're going to get easier math. Don't worry. We did a pretty good job for most of the rest of this live stream. But at this particular point, I guess we did go a little bit over the deep end. All right, well, let's see, just to finish off with this thing. Let me just finish off with one question. Mithun Pet Shiraj asked, what writing tool do you use? I just use a stylus here, and it happens to be drawing on a tablet. And when I draw on the tablet, it pipes the image all the way into a computer. The computer merges the image together with what the camera is sending. That's called a green screen. And then I can play weatherman. I just point at stuff like the weatherman. And then what happens in the end is you get this live stream, which we make by putting everything together. We designed this because I've been doing online teaching for a while before, and we found this to be the most efficient way to try to show something to everybody. All right, I think at that point we basically have run out of the time for today, and I want to thank everyone for putting up with our blend of mathematics, which started with things that were maybe a bit more on the approachable side. So that proves that we can do that. And at the end, it also proves that I have this bad habit of sometimes trying to tell you the answer, where it uses like some more advanced mathematics. But hopefully you got to see something neat through it. And now you know what the squiggly thing means. All right. Well, see you guys all tomorrow. I'll be back at 4 o'clock, and we will do a better job of trying to get easier problems. See you there.